In this video, we're going to take a look at the next gas law, which is Boyle's Law. So Boyle's Law is different from Charles' Law in that this takes place at constant temperature. So this time the temperature is going to be staying the same. And we're going to be looking at what happens to the relationship between volume and pressure. So volume and pressure are inversely proportional to each other. So what that basically means is that, let's say, for example, pressure goes up, then volume goes down. So they're going in the direction of they have opposite direction. They move in opposite directions. Proportional meant they moved in the same direction. So for Charles' Law, if one went up, the other one went up. Over here, inversely proportional means they move in opposite directions. One goes up, one comes down. So generally what happens is that if the volume of a gas is decreased, then the pressure of the gas increases and vice versa. So remember, the amount of gas is still constant, and so is the temperature. You can represent Boyle's relationship by stating that the volume is proportional to 1 over P, to 1 over P. So that essentially means that they're inversely proportional. Volume is inversely proportional to pressure. So if you decrease the volume, you increase the pressure. The formula for Boyle's Law is the P1 V1 is equal to P2 V2. And the ones are all your initial values. So this is your initial pressure, what you start off with. The V1 is your initial volume. The P2 is your final pressure, or your new pressure. And the V2 is your final volume. Final volume. So here is a graph representing the relationship between volume and pressure. You can see that as you increase the volume over here, that the pressure goes down. So for example, let's say we had a volume of 5 mils. The pressure at 5 mils is about 39. If you then, let's just say you want to quadruple, or no, let's say you want to quadruple the volume. So we'll go to 20 as your volume. At 20, the pressure is about 9.8, close to 10. So as you saw there, when we quadrupled it, the volume, the pressure basically became a quarter of what it was before. So if you, let's say, doubled the volume, you would half the pressure. It's divided by 2. If you quadruple the volume, well, you divide the pressure by 4. So in that sense, they're inversely proportional to each other. Now, this graph is a bit difficult to read because it's curved. So what we often do to represent Boyle's Law is we use a different graph, and I'll show you that graph over here in your presentation. We do the volume. As you can see over here, we have our volume right here. And we have over here, instead of pressure, we have 1 over pressure. And so as you increase the volume, 1 over pressure goes up. Which basically means that at a higher volume level, so let's say at a volume of 35, 1 over pressure is a higher value over here. And that's the same relationship, because 1 over pressure will be higher at a higher volume because your pressure itself is lower. If you're at a lower volume, your pressure is higher, so 1 over pressure is going to be a lower number. So this is just a way to turn this graph into more of a linear graph, essentially. But they both express the same thing. Just pay attention to the unit. As you can see here, as volume goes up, pressure goes down, inversely proportional to each other. So let's go take a look at explaining Boyle's Law with the kinetic molecular theory. So as we saw, if you increase the volume, well, then the pressure will decrease because they are inversely proportional to each other. So increase volume, pressure goes down. If you decrease the volume, then you increase the pressure. Pressure increases. So you decrease volume, pressure goes up. And so why is all this? Well, so let's say you're increasing the volume, pressure goes down because if you have a larger volume, what that means is that the particles have more space and will therefore collide less often with the walls of their container. They're not as crammed as they were before. So if you've increased the volume, for example, like you do over here, the particles are not as crammed and they're not all colliding with into each other as often, into the walls of the container as often. But if you decrease the volume, so let's say you push this piston down, now all the particles are all crammed together and they're basically hitting each other and bouncing off the walls more frequently. And as a result, there's a higher pressure recorded. So that's why they are inversely proportional to each other. You decrease volume, they're crammed, more pressure. Increase volume, they're not so crammed, less pressure. So let's do a couple practice problems relating to the Boyle's Law. We'll start off with this example over here. So we have a weather balloon with a volume of 2.00 times 10 to the power of 3 liters and a pressure of 96.3 kPa. And it rises to an altitude of 1 times 10 to the power of 3 meters. So it goes higher up, about 1,000 meters up, where the pressure is 60.8 kilopascals. And so assuming there's no change in temperature or the amount of gas, what's the final volume of the weather balloon? So let's write down some given information that we have. We have that our initial volume for the weather balloon is 2.00 times 10 to the power of 3 liters. We also have that our initial pressure is 96.3 kilopascals. And we are also told that the balloon rises to an area in the atmosphere where the pressure has decreased. The pressure has decreased. And so if the pressure has decreased, we would expect that our second volume, that the volume should increase because the particles can space out a little bit more and take up more space. They won't be as crammed. So what we're going to do is we're going to go ahead and calculate that V2 to see if it's actually a larger volume now that our pressure has decreased. So our unknown is our V2. And we know that this is one of those relationships between pressure and volume. And as we saw previously, when we're looking at the relationship between pressure and volume, it's an inverse relationship. So volume is going to be inversely proportional to pressure. So it's basically proportional to 1 over P. Okay, so volume is proportional to 1 over P. It's inversely proportional to pressure, in other words. And so we're going to write out our equation. The equation is P1 V1 is equal to P2 V2. And, well, actually, that was our equation there. I don't have to write E twice because it's our guess method I'm doing here. And I'm going to go ahead and plug some values in and then solve. So we have P1, which is 96.3 kilopascals, multiplied by our V1, which is 2.00 times 10 to the power of 3 liters, which is equal to our 60.8 kilopascals times our V2. And if we want to solve for V2, we simply divide everything by 60.8 kilopascals. So that's going to be V2 is equal to 96.3 kilopascals times 2.00 times 10 to the power of 3 liters over 60.8 kilopascals. We can cross those units of pressure out, and we're left with a volume. So we get 96.3 times our 2.0 times 10 to the power of 3 there, divided by 60.8, and we get approximately 3,167.763158 liters. But we have to have a therefore statement, and we have to have the proper number of significant figures. So therefore, the final volume is approximately, it looks like 3 sig figs is what we need. So we can round up to 3,170 liters. And this makes sense because this is larger than our 2,000 liters that we had before. So the pressure went down, and the volume therefore went up compared to V1. And so that was an example using Boyle's law. Let's do one more example together over here. So we have a balloon with a volume of 2 liters. It's filled with a gas at 3 atm. If the pressure is reduced to 0.5 atm without a change in temperature, what would the volume of the balloon be? So we have some given information. We have our V1 over here is 2.0 liters. We have our P1 is 3 atm. We have our V2. It is, we're looking for what the new volume is going to be. So we don't know what that is. And then we have our P2. So we reduced the pressure. And so if we reduce the pressure, think about what that means for volume. Volume should go up. It should be higher than 2 liters at the end. We're being asked to find that new volume, V2. And the equation we're going to use, we know that it relates to Boyle's law because it's an equation where the volume is proportional to 1 over P, or in other words, it's going to be inversely proportional to the pressure. So our equation is going to be that P1 V1 is equal to P2 V2. And so we can go ahead and substitute and then solve for our V2. So we have 3 atm times 2.0 liters is equal to 0.5 atm times V2. And so we can simply solve for V2. So V2 is equal to 3 atm times 2.0 liters over 0.5 atm. Cross atm's out, and you get your 3 times 2, and then divided by 0.5 is 12 liters. And you can see we have 1 sig fig is our smallest amount there. So we're going to do therefore, the V2 is approximately, we can round down to 10 liters to get 1 sig fig. And this makes sense. We said the volume should increase because we decreased our pressure. So we decreased our pressure, therefore volume should go up compared to the 2 liters that it was before. And so that was our second example with Boyle's law. There's another demonstration I would like you to watch. This is for Boyle's law this time, so you can watch it in this video here, and make a label diagram to explain how the demonstration works and how it works and how it's an application of Boyle's law. One very interesting application of Boyle's law, a real-world application of Boyle's law, is using a syringe to, let's say, withdraw or suck up some fluid, for example, from this vaccine over here. So what you do is you basically pull back on the syringe like this, and that's going to increase the volume in the syringe. And so because you're increasing the volume in the syringe, what you're doing is you're reducing the pressure in the syringe. And so because you're reducing the pressure in the syringe, that's going to cause the fluid to basically be sucked up or pushed into the syringe as you're pulling the piston upwards to increase this volume. And so that's an application of Boyle's law that you can see in everyday life. And please make sure you take a look at that demonstration to understand it, summarize it, and draw a label diagram of it.